Hello there, physicists! Welcome back. Today, I am going to talk to you about base units and conversions. So, to begin, it's important to understand that as a physicist, we need to always remind ourselves, even though we do a lot of math, there's something that separates us from the math people. And it is the fact that when we work with numbers, they will never be naked. Now, what I mean by that is we will always have a unit associated with our numbers so that we are reminded of what physical meaning those numbers have. So, to begin, let's look at what are going to be our fundamental units, also known as the base units in physics. You've probably heard of some of these before. So let's start by talking about the base units of length. In the usual system, with what we call English units, you probably know that the base unit for length is the foot. And you would be right. I would say, good job, Johnny, except for one problem. Dun dun dun. We, being the United States, are a tad backwards. We use a system of units that the rest of the world doesn't use. In fact, I'm going to take a time out here and show you this map of the world. Every country in green uses what's called the Standard International System of Units. This is sometimes referred to as the metric system. And you may notice that there is this little country over here that we happen to live in that's not highlighted green. There are a couple of exceptions. There's a small country here in West Africa, and there is a southeastern country as well that also uses English units. But more or less, we're kind of strange compared to the rest of the world. And guess what? Physics is an international endeavor. Therefore, we do not use English units really in physics. Instead, we tend to use those standard international units or metric units. So as far as our course is concerned, the base unit for length is actually going to be the meter, denoted with a lowercase m. Good. Next, for mass. Let's start with our standard international units here. If we were in class and I said, Johnny, what's the base unit for mass? Johnny would go, oh, I know, it's the gram. And I would say, Johnny, you poor soul, you took chemistry. I'm sorry, but the gram is not the base unit of mass. In chemistry, I know you worked with grams frequently. However, the truth is we actually have the kilogram as our base unit, or 1,000 grams. And we denote that with a kg. So we work in kilograms when it comes to physics. And if I ask Johnny again, what's the English unit for mass? Johnny would go, the pound? And I would say, no, Johnny, it's not the pound. That's a unit of force. And then Johnny would go, well, maybe it's the ton? And I would say, no, Johnny, that's another way to measure force in English units. And then Johnny would go, well, I don't know. And I would tell Johnny that you measure mass in English units with these. Yes, that is a slug. The English unit for mass is a slug. U. So, theoretically, when we're done learning about conversions, you can actually determine how many slugs you are. Gross. And lastly, our major base dimension and therefore base unit is how we measure time. And time is kind of nice. Time is universal. Both English and SI units for time are the second. denoted with a lowercase s. So there you have the base units. And again, keep in mind that as far as we are concerned, all these English units are used mostly in engineering. So if you ever become an engineer, yes, you will deal with these units, but in this course, we deal with strictly SI units. So get used to seeing and using the units of meter, kilogram, and second. Now that we have discovered and gone over the base units that we'll be using in physics, oftentimes, especially in a lab setting where we're collecting data, we will have to convert our units. So we need to get into the practice of being able to do unit conversions. So I have a 3-step process that we're going to go through, and it's just going to repeat. I'm going to give you a total of 4 or 5 examples here. The process is the same pretty much every time. All that's changing is either the degree of difficulty in the conversion or the nature of the conversion. So, to begin, my first problem I have for us is converting 12 millimeters into a certain number of meters. And if we were in class and I said, hey, Johnny, how am I going to do this? Johnny may go, oh, Mr. H, that's really easy. All I have to do is move the decimal point 3 places to the left, like this. 1, 2, 3, and we're done. And I would say, Johnny, I'm sorry, but you're just not doing physics. You're doing some crazy voodoo math here. And I'm going to tell you right now, I am going to strongly discourage moving the decimal point as a way of converting units, because it only works for a handful of cases. I would rather you be well equipped at converting from any form of unit into any other form of unit. And the process I'm about to show you is universal. It can work in any situation when it comes to unit conversions. So step 1 in my process is declaring what is my conversion factor. In other words, how can I relate the units of millimeters to the unit of meters? Another way to think of this is to ask the question, how many millimeters make 1 meter? And the answer is 1,000 millimeters is the same or equal to 1 meter. That right there is what we call the conversion factor, the relationship between the units I currently have and the units I'm trying to get my data into. Okay, so now that we have our conversion factor, here's the next step. I'm going to take those 12 millimeters and I'm going to multiply them by my conversion factor, and I'm going to put it in the form of a fraction. Now, I got to be careful because there are 2 ways in which I could make my conversion factor into a fraction. I could put the millimeters in the numerator, or I could put the meters in the numerator. And the choice I want to make is so that my millimeters cancel out, because I want my final answer to be just in meters. Well, the only way to do that is for me to put my millimeters in the denominator. So they will go right there, which means by default my meters for my conversion factor will go in the numerator. And if you want to, if you find it helpful, you can always put the quantity you're starting with, in this case the 12 millimeters, over a 1, just to remind you that yes, this starting quantity is in fact in the numerator. Alright, so now we have it all set up. Last thing we have to do is just multiply. So when we do that, we're going to be basically multiplying the numerators together, and we will be multiplying the denominators together. And as a result, we will end up with 12 millimeters times 1 meter all over 1 times 1,000 millimeters. And if you know your algebra, well, we have a millimeter in the numerator, we have a millimeter in the denominator. They cancel, and all I'm left with is units of meters. From here, it's just basic math. 12 times 1 gives me 12 in the numerator over 1,000 in the denominator. And my final answer, therefore, comes out to be 0.012 meters. Now we get the same answer as if we had done the little voodoo magic there. Yes. And maybe this process was a little longer in this case. Yes, I agree with that. However, in the future examples, you're going to see that this process is actually, it's kind of higher level. It's more advantageous than just moving the decimal point to do a conversion. So there is your first example. For our next example, we're going to do a conversion where we will need to use multiple conversion factors. So in this instance, we're going to want to take 2 days and somehow, some way, get it converted into seconds. Now, how many of you out there know how many seconds are in a day? I imagine not too many hands would be raised there. So we're going to go with some more commonly known conversion factors in combination to ultimately get us from days into seconds. While many of us may not know how many seconds are in a day, I'm willing to bet a lot of us know how many hours are in a day. You would say that 24 hours is the same thing as a single day. So this would get us from days to hours. Now, from there, we can say how many seconds are in an hour. And I recommend that you actually memorize this conversion factor because it saves you the intermediate step of going from hours to minutes and then minutes to seconds. There are 3,600 seconds in 1 hour. So now we have a total of 2 conversion factors to use. The 24 hours in a day, and then the 3,600 seconds in an hour. From here, the process will be exactly the same. It's just now I'm going to be multiplying by 2 conversion factors instead of 1. So I'm going to start with my 2 days, and I'm going to multiply by my conversion factor to get from days into hours. I'm going to want to put my days on the denominator and my hours in the numerator. Okay, and then the next step will be to multiply by my second conversion factor so that I get those hours into seconds. And based on the fact that hours are in the numerator here, that means for it to cancel, I'll need to put hours in the denominator down here and seconds in the numerator like so. And now you can see how the days will cancel here, the hours will cancel there, and the only units we are left with are seconds. And now, like the prior example, it's just a matter of doing the multiplication. And I'll spare you the nitty-gritty details of that. You can check this computation if you wish. But what you end up with is 172,800 seconds. Now, at this point, you might say, Mr. H, what are we doing with significant figures here? The last 3 days, we've discussed how to account for significant figures when we're doing anything in physics. And you have a point. If we were technically following the rules for significant figures here, we would have to somehow round our final answer of 172,800 seconds so that it had only one significant figure based on the math we did here. However, these conversion factors that we're looking at, they are exact values. We know that there are exactly 3,600 seconds in 1 hour. We know there's exactly 24 hours in a day. And because these are known exact values, they kind of dance around the rules for significant figures. Sig figs will be mostly important when we're taking data for a lab. Our next example will demonstrate how to convert units when we have multiple forms of units associated with a number. For the example I'll be showing you, I will be converting 70 kilometers per hour into meters per second. This is actually a fairly common conversion that you will see in our next two units that we're going to do. So the way to tackle this is to come up with conversion factors for each set of units. First, I'm going to need a conversion factor for converting the unit of distance here, kilometers, into meters. And I will need another conversion factor to convert the units of time that I'm starting with, hours, into seconds. So let's establish what those conversion factors are. We will have the conversion factor of 1,000 meters being equal to 1 kilometer, and also the conversion factor of 3,600 seconds being the same as a single hour. From here, we just need to line up these conversion factors and multiply them by our 70 kilometers per hour. And if we set everything up perfectly, we will ultimately end up with meters per second. So here we go. 70 kilometers per hour. And it's important to note here that if we really wanted to make sure that we were doing this properly, the 70 actually goes in the numerator. In fact, when we talk about any sort of per, 70 miles per hour, 70 meters per second, the per means division. So if we wanted to express this properly as a fraction, it really is 70 kilometers over every 1 hour, or per 1 hour. This will make our setup a little easier when we write in our conversion factors. So here we go. I need to get the kilometers into meters, so that means that my distance conversion factor, the kilometers must be in the denominator so that they cancel, and my meters will be in the numerator. And then for the time portion of this conversion, the hours are in the denominator, so that means I must put my 1 hour over here in the numerator and my 3,600 seconds actually in the denominator. So I would say the key step here is to make sure when you have a value like this with multiple units in it, make sure you are expressing it properly as a fraction first. It then makes it much easier to see how you're going to set up your conversion factors as fractions as well. So we see here my hours will cancel, one in the numerator, one in the denominator. Same thing with my kilometers. There we go. Whoops, lost them for a minute. And all we are left with are meters in the numerator and seconds in the denominator. So we're in good shape. Again, I will spare you the ugly mathematics and let you know that we end up with 19.4 repeating meters per second. And if we wanted to, we could certainly round that to whatever we wish. Again, the significant figures rules aren't overly significant here. If we wanted to technically follow the rules, we would want to probably put this to 2 sig figs and call it 20 meters per second. But either way, the process is the most important thing to take away from these examples. Now, physicists, I give you your last example. And this one is the most trickiest, the most counterintuitive for students to get. we're going to take something that has multiple dimensions of length and convert it into another unit with multiple dimensions of length. In this case, we're going to be taking what we would consider a surface area of centimeters squared and converting it into units of surface area that are meters squared. So here we go. We already know that we're probably going to want a conversion factor connecting centimeters to meters, and that would be the fact that there are 100 centimeters for every 1 meter. However, that isn't really what we want. That would be great if we were talking about units for a single length. Instead, we're talking about units for a length times another length, or lengths squared. The way to ultimately figure out what our conversion factor will be is to take each side of the conversion factor and actually square them. And what will come from this is everything inside the parentheses will be squared out, including the number that we have, as well as the units themselves. So 100 centimeters squared will actually become 100 squared times centimeters squared. And that'll be equal to 1 squared times meters squared. Now we have a number in centimeters squared being equal to a number in meters squared. Now I have my desired conversion factor. So that's the little twist to when you're doing any sort of conversion involving surface area or even volume. So now we set it up like any other problem that we've done in the past. 47 centimeters squared, and we'll multiply by our conversion factor. I'm trying to eliminate the centimeters squared, which means I will put the 100 squared centimeters squared in my denominator and the 1 squared meters squared in the numerator. My centimeters squared will cancel, leaving me with units of meters squared, and then it's just math. That's all it is. And we end up with 0.0047 meters squared as our final converted answer. And that's it, physicists. These are pretty much an accurate cross-section of all different combinations of conversions that you may have to do. Please take 10 to 15 minutes to go back to these examples, observe any that you may have had problems with, jot down any questions in the appropriate space on your note-taking guide, and be ready to ask questions for tomorrow, because we did do a lot in this session. And we're going to be doing a lot more with unit conversions in class tomorrow. So with that said, physicists, till next time.